Good evening and welcome. Tonight I'm going to take you on what I hope will be a journey of discovery that will inspire at least some of you to go home and try some of the things that I'm going to show you this evening on for yourselves. Astronomy is one of the few sciences that has a long history of people around the globe looking up in the sky and going, wow, and then going out and discovering something completely new that no one else has ever known about. Well, in a lot of sciences, this self-discovery, this amateur astronomy, this citizen science, this amateur science, stopped at the turn of the last century. In astronomy, it continues today. And even today, regular people living regular lives, working as teachers, as plumbers, as pipe fitters, they're still going out and making some of the most phenomenal discoveries of what's new and great in this universe all around us. So I'd like to start by looking up. Let's start by stepping out of this room and reaching for the stars. Optical astronomy, the thing I'm going to talk about most tonight, is first and foremost a science that relies on telescopic observations of the universe around us. When thinking of telescopes, a couple different things may come to mind. You might envision a giant dome squatting on the side of a mountain, sort of like a giant optical R2-D2. Your mind's eye might see a small portable telescope set up outside in a parking lot with little kids from a local school looking through it. Or you might envision a local observatory at a state or national park where amateur astronomers act as the docents. No matter what you're envisioning, you're seeing a tool that's useful for discovery. The multimeter class telescopes and their on-orbit professional brethren are powerful tools designed to probe the faintest stars in the most distant galaxies. Getting time on these telescopes is a difficult process that requires competitive applications for time, and the most brilliant astronomers in the world are often lucky to get granted a few dozen orbits in a lifetime. Time on these telescopes is generally used to study objects that will reveal their science in the shortest amount of time, or to study objects that you can study in absolutely no other way. Backyard and educational telescopes, however, these are the tools of individuals who can go out and choose to look up at whatever they want. These are people who can observe 100 objects in one night doing a Messier marathon, or they can choose to observe the exact same objects night after night after night over the course of a lifetime. Their work can be used to study long-term changes in our inconstant skies, and their telescopes are actually the workhorses that plow through the celestial sphere and look for unusual behavior that can only be noticed if you look at the same thing over and over again to notice the slight, rare, not often seen with one brief glance changes that occur. These images, these come from a high school in Massachusetts, a high school in the city of Boston, which is a large, light-polluted city. These are pictures that were taken by a technician at the Dexter Southfield Junior-Senior High, where they have a 0.7-meter telescope. This telescope, run by a high school, has taken the clearest pictures taken from anywhere on the ground without using special techniques called adaptive optics that flex the mirror to help compensate for the atmosphere. These are images of the moon going behind Mars, or rather the Mars going behind the moon. Sorry, the other would be much more interesting, but doesn't happen. Images of a nearby nebula, and images of our own International Space Station, where you can actually make out the individual solar panels. Now, can you imagine being the high school student out there taking these images? These are things that anyone can do. And that's the great thing about astronomy. One of the organizations that works very hard to bridge between professional and amateur astronomers, amateur being defined as basically anyone who earns their money doing something else, The organization that works the hardest to bring these two populations together is the American Association of Variable Star Observers, which is an organization that I'm proud to sit on the board of. The AVSO is a scientific nonprofit dedicated to the study of celestial objects that vary in optical brightness. This can mean a lot of different things. In some cases, when these objects vary in brightness, it's because the object itself is actually expanding and contracting, breathing as it becomes unbalanced between light pushing outward from the center of the star and gravity pushing inwards. This is something we don't think about a lot, but light actually pushes on you, pushes out. In the center of stars, there are giant nuclear reactors. The core of a star burns to generate heat, to generate light. And as this light pushes out from the center of the star, it holds out the star's atmosphere, which is trying to collapse in with gravity. In some cases, the star becomes unbalanced due to a lot of complicated processes I'm not going to torture you with. But if you ever take an upper division astronomy class with stellar atmospheres, you might be forced to learn this. It has to do with helium ionization. In some stars, as the light presses out, as the star evolves and it heats up in its evolution, stars change. It reaches a point where it becomes unbalanced, and it pushes a little bit too far out, and the atmosphere cools a bit. And then it compresses back in, and it heats up. And then it goes back out. And the star ends up regularly, for millions of years, contracting and expanding night after night, week after week. And we can see these changes from here on the planet Earth. Other changes that we see, we call a variable star a binary star. It's two stars, but that's still, when we look at it, we see it often as one star because these two objects are so far away you can't see them as two objects. But what you see is a really bright object that as a smaller object passes in front of it, a smaller, fainter object passes in front of it. It's like a person walking in front of a spotlight. Yeah, you can still see the spotlight, but the total amount of light coming off of that spotlight gets a little bit lower for a small amount of time while that person walks past. This is how we observe binary stars, as changes in brightness as one star passes in front of the other. And in other cases, we even count supernova, which vary once, very radically. We count supernova as variable stars. And at the American Association of Variable Star Observers, we're dedicated to moving in three different directions: in education, in mediating professional amateur astronomy collaborations, and in archiving the data. As educators, we use variable star astronomy to teach universal concepts, the ideas of orbits, the ideas of things pulsing in and out. For those of you studying physics, it's just a harmonic oscillator. It's just a simple harmonic oscillator in some cases. We use the concepts of astronomy, which are really exciting, particularly to 5-year-olds, unless they're into dinosaurs. We use these concepts to get people excited about astronomy. Astronomy can be a gateway drug to learning other sciences. As mediators of pro-am collaboration, we work to take backyard astronomers, people who have an 8-inch telescope in their backyard and just want to go out. And with an 8-inch telescope, it's actually possible to observe a planet passing in front of a star in a distant solar system. You can do that with an 8-inch telescope that you can buy for a couple $1,000s, or less if you get lucky, and even free if you happen to find the right person who's cleaning out their closet. You can observe planets around other stars. And we work to take these people and to match them up with professional astronomers who just need data. As a professional astronomer, I can't go to a national facility and say, I need 100 nights all by myself to study 10 stars, but that's what my research requires. But I can go to a group of amateurs and say, hey guys, it's unfortunately mostly guys, women in the room, we need you in amateur astronomy. I go to these people and I say, join me, help me, let's create science together. I currently have drafts of 2 papers sitting on my hard drive that will hopefully get submitted in the next couple of weeks, where all of the data taken for both of the papers was taken by amateur astronomers using equipment they bought and are using in their backyard. Here I showcase a bunch of different patterns. I'm going to go on and explain all of these in detail. But one thing I want to point out to you, because this is the only place that it crops up, and I don't seem to have a laser pointer, so I'm going to try and get my pointer over there. There we go. This squiggly line up here that blurs out, this is 150 years of observations of one variable star. It's called Myra. There have been people since 1850 going out, looking up, and writing down how bright they see this star. This isn't the only one, but this is perhaps the most popular. I want to talk about these stars for a moment. These are stars that you don't need to look at with a telescope with a fancy camera. You don't even need a telescope or binoculars. Some of these bright red stars are close enough that you can just go out tonight and look up with your eyes. And if the moon is down, and I unfortunately have to admit I've been traveling too much to remember what the moon is doing, but I think we have only half a moon or less right now. It's full moon? Waxing gibbous, I'm being told. Oh, okay, don't look tonight. Wait a few days. You can go out, and these things vary by what we call 2.5 magnitudes. Now, the magnitude system's kind of screwed up. 0 is really bright. 6 is the faintest thing that you can see with your eyes, and it works logarithmically. I live in St. Louis right now, and the brightest you can see with your eye in a city like St. Louis, which isn't huge, but it's a city. Most of the time it thinks it's a city. You can see down to 4th magnitude. So if you've ever looked up while standing near the stadium when the lights are on, you can probably see down to about 4th magnitude. A change of 2.5 magnitudes. This is the equivalent in difference in how much light is coming off of going from looking at a 7-watt Christmas light, this is one of the big ones you put on the outside of your house, to a 40-watt desk light. Now, is there anyone in this room that cannot tell the difference between the amount of light coming off of a Christmas light bulb and a 40-watt desk light? So if you were asked to go out and look up at a star and go, so does it look like the Christmas tree light tonight or like the desk light tonight? That's something everyone can do. And people have been doing this in their spare time. And what's cool about these stars is they vary in brightness very slowly. Some of them have periods of 100 days, some of them have periods of 400 days. And so you go out and you're standing there waiting for your dog to do whatever, you're going out, you're waiting for someone to pick you up, and you look up and you find your bright red star and you compare it to the brightness of other stars in the sky that aren't changing in brightness. And you write that number down. You stick it in your cell phone, you stick it on your Palm Pilot, you write it in a notebook if you like notebooks. And then you can report it over the internet. One observation a night is all that's needed of these things. And over 150 years, we can build an understanding. And we've learned a lot from people going out and looking at these really bright red stars. Here's another example in this image. You can actually see the stars so bright that it overwhelmed the camera that was looking at it. This particular star has a 426-day period. And looking at this, you can see it gets bright fairly quickly and then takes a little bit more time to get fainter again. You can see that it's erratic in how high it gets. And we know that this is normal for this period of a star. And so we kept looking, and we looked at some more examples over 100 years or so. And we learned that the stars at the top that have about 150-day periods, they look like nice, friendly sine waves. We learned that the ones with 300-day periods, they alternate in height, going from tall to short, over and over and over again. And we learned that you get weird bumps and wiggles and erratic heights when you look at the ones that are around 400 days. We learned all of this and even more because we found some of them have these crazy mixing of periods where you start to have to use Fourier analysis and do complicated mathematics to figure out what all is going on as this harmonic oscillator does crazy things. We learned everything that we know from In these cases, 41 years or more of data from regular people going outside and looking up and writing down what they saw. They take what they wrote down and they email it, they mail it. In some cases, they just mail their whole notebook to the AAVSO, and we store it, and we stick it in computers, and we archive it. And when a scientist is ready to sit down and analyze all of the data, we have it for them to do. And so this is a wonderful collaboration between the public and between the professionals, where in many cases the data they're using took longer than they've been alive to acquire. How do you write the letter saying, "Dear NASA, I need enough time on telescope X, and by the way, I'll be dead by the time all this data is collected"? We've solved that problem, although it's kind of creepy to realize you're using data from dead people. Biologists are far more used to that problem. Now, in other cases, we're dealing with stars that are much more exciting. And instead of looking at them every single night, you just look at them once because that's the only chance you've got. These are gamma ray bursts. Now, these you'll never see. Gamma ray bursts come in two different genres. There are those that involve black hole and neutron star or other black hole or two neutron stars, two extremely heavy objects that weigh many more times the mass of the sun that decide to merge. In the process of spiraling together, coming together, merging, they give off this huge burst of energy. For 3 seconds or so, they're giving off more light than the entire Milky Way galaxy. They're bright, but they fade very, very quickly. The light that they give off in gamma ray light, gamma rays, it's a color. We don't usually think of X-rays, gamma rays, radio as color, but that's all they are. When you tune in your favorite radio station, you're just tuning your radio to a specific color that your eyes can't see. And we're probably glad that we can't see radio, because otherwise all of your cell phones would be little flashlights all of the time. All of your wireless antennas would be little beacons of light, and your radio stations would be making it impossible for you to see anything. Gamma ray is just a really blue color, so blue that it's beyond the ability of your eyes to even contemplate detecting, and in fact so blue that it's capable of destroying human body cells. But luckily it can't get through the Earth's atmosphere, so we're fine. But there are satellites on orbit that detect these bursts. And when they detect these short 3-second ones or so, we don't generally get the chance to see the fading light. But then there's another one. And in these cases, we do get to see them. They last longer. And here we see an image from a Buffalo Astronomy Club. Let me explain to you how the longer ones work. In this case, you have a giant star. If any of you have a chance to go to the southern hemisphere, there's a star that you'll be able to see, Eta Carina. This is a giant, angry star undergoing weird things no one understands. It's probably going to be the next star to explode that we'll get to see. This means that someone in the southern hemisphere might go out tomorrow and notice it exploded, or someone 10,000 years might go out and notice it exploded. It's astronomy. 10,000 years is a short period of time. But when this star goes, and I'm going to see if I can make this animation go again, always a challenge. It won't let me. Okay. When these giant stars go, when these hypernovae go off, in some cases, they beam energy out their poles. And if you happen to be located within the cone of that flashlight beam, and you're too close, you die. 7,000 parsecs we think is the death limit, which is a bit worrisome because Eta Carina is within 7,000 parsecs of the Earth. Now, luckily, its beams will be pointed somewhere else, so we're fine. Again, no death known coming soon. But there might be other worlds that could get their atmospheres ionized along those beams. Huge amounts of light go out in gamma rays, in X-rays. And that light coming out of the beams we detect as gamma ray bursts. And then a few weeks later, we see the supernova coming off. And this is a really neat process that we have the public involved in observing. So the way it works is, so here's the initial gamma ray burst at the same point that this flash of gamma rays is coming off. There's a momentary, extraordinarily bright flash of optical light as well, and it rapidly fades. Magnitudes in minutes. So this is basically like taking a dimmer switch and just turning a dimmer switch on such that you go from floodlight at the local car station to lightning bug on the surface of the moon in the course of a few hours. That's the change in brightness. 10 feet from giant floodlight, lightning bug on moon. Now, what's kind of neat, what allows us to observe this stuff, is we have all these satellites in orbit, denoted by yellow boxes. And these orbiting yellow boxes that are really high technology pieces of equipment, when they detect the gamma ray bursts, they quickly zero in and figure out where the optical burst is as well. And then they beam those coordinates, the position on the sky, down to amateur astronomers and professional astronomers across the globe. And all of these people who are getting these bits of information in text messages, in emails, in pop-up boxes, all sorts of different ways. They're told, go look right now. And we tell the world, because someone's going to have clouds, someone's telescope is going to be broken, someone's going to be pointed entirely in the wrong part of the sky, and some telescopes take time to slew. But if we tell everyone who's interested and has signed up to get the SMS text messages, someone will be able to get their telescope pointed and follow up in optical light and see what's going on. Now, this happens. There are amateur astronomers around the globe who'll sit down and they can't figure out what they want to look at with their telescope that night. So they'll dial up on the internet one of the NASA satellites and they'll say, okay, so the SWIFT satellite, that's one of the gamma ray burst detectors, is looking in this section of the sky. There's some pretty nebula over here. I'll look at those nebulas and hopefully a gamma ray burst will be discovered. And then what they'll do based on this decision is once the gamma ray burst goes off, they might be pointed right here and the gamma ray burst is right here. And that movement of their telescope might take 2 or 3 seconds. They will be the first telescope on the planet pointed at this new discovery. And there's a man in Finland, Arto Oksana, who's responsible for discovering several different of these objects from the ground and following them up. And this is really important because when these objects are at their brightest, you can't point a professional telescope at them. You take a telescope that's 4 meters in diameter, 10 meters in diameter, and you put a lightning bug in front of it on the Earth, flying past it, and it wipes out the detectors. Suddenly you can't see anything else that's too bright of a light. You point that telescope at one of these gamma ray bursts and you're going to break something. Now at the same time, the folks who've been granted time on these telescopes, they filled out paperwork that probably took them 3 weeks to fill out to get that night of time on that telescope. And then they're counting on that data to do the next 6 months of research. And they have to do that research to write their next paper, to do everything related to answering some question that's extremely important to them, to getting the next paper that will help them get the next promotion. This is their job, their career, their dream, all tied up at once. And now you're telling them, point the telescope at a gamma ray burst that has nothing to do with your research. And they're going to hem, and they're going to haw, and they're going to do it because they have to, but they're not going to do it quickly. So by the time they take these giant multi-mirror telescopes that do not move quickly and slew them across the sky, some of them making backup noises like a school bus backing up, so they slew them across the sky and point them at the gamma ray bursts. This is about the point in time the gamma ray bursts are often too faint to be seen with the amateur telescopes anymore. So it's a handoff process, where the amateurs with their backyard telescopes, and in this case I'm actually including undergrads because there's a lot of undergraduate universities that belong to the gamma ray burst network, which is run out of Sonoma State University. These people observe it with their small telescopes, their under a meter telescopes, and then hand it off to the bigger boys a few minutes later, a few hours later. It's a collaboration. And this collaboration is allowing us to learn new things about how our universe works. Back in 1998, the astronomical community was sort of spun around and dangled upside down by completely new understandings. We'd been taught forever that there were three fates for the universe, that it would either have so much stuff in it that would expand for a while, and then the gravity of all of that stuff would cause the universe to collapse back down, and we'd die by fire. We'd die in a great crunch. Or alternatively, there wasn't enough stuff in the universe, and we just keep expanding apart forever, nothing slowing down the expansion of the universe, and we'd basically die by ice. We die by energy death as everything gets spread out and cooled off. Or somewhere in the middle, if you hit a perfect balance of mass, the universe, given infinite time, would stop, which is kind of cool, but since infinity doesn't exist, we'd never quite get there. But in 1998, we discovered we were wrong, and the math suddenly got much, much harder, because we discovered that there's this extra thing in this universe. And when astronomers don't know what something is, we have a tendency to name it dark, then throw in a noun. So we have dark matter, which is the matter we don't know what is, and now we have dark energy, which is the stuff that is causing the universe to accelerate apart. And that means that the universe is essentially going to accelerate apart to the point that someday we won't be able to see any of the rest of the universe except for the stuff that we're gravitationally attached to, and that's kind of cool, but really the subject for another talk. Now, the whole fact that the universe is not just expanding, but its expansion is accelerating is really cool. And we understand this by looking at supernova. That was where the original 1998 observations came from. But in this particular plot, you can only see supernova to right here. We can't see supernova out very far. They're bright, they're really bright, but they're not as bright as gamma ray bursts. So if we want to probe the most distant corners of the universe, we have to figure out how to use gamma ray bursts to map our universe. There's a man down at Louisiana State University who's working to figure out how to do that, and these results are preliminary and they need to be repeated, and we need more data. But his early data indicates the universe might not just be accelerating apart, but that acceleration might be accelerating. That's sort of like you're in a car and you floor it so you're accelerating, and then you stick a rocket pack on to accelerate your acceleration. Our universe just might shred itself to bits someday in the distant future, but we'll already be dead, so it's okay. The universe is all trying to kill us all the time. Astronomy is really the study of how, really, we don't know why we're alive, because the universe is trying to kill you right now. You just luckily aren't aware of it. Now, in order to study the evolution of the universe, we study gamma ray bursts. But we're also interested in not just the most distant supernova and gamma ray bursts, which come from supernova, but also in the nearby stuff. We don't often think of it this way, but we're made of stardust. Everything that you have that is made of gold, made of silver, made of anything that's heavier than iron, that's all, or lead, I'm sorry, I just had a chemistry moment. I think I'm getting old. Anything heavier than the chemical element Fe, which just totally fell out of my brain, this is highly embarrassing, that all came strictly from supernova explosions. That means that in order to get your engagement ring, to get your necklace, to get your class ring, a star had to explode. That material had to get mixed throughout the universe. That material had to get mixed into a star that was forming, had to get mixed into a planet was forming. To understand the generation of all of these heavy elements, we have to understand how stars die. We have to understand how in some cases they explode radically. And so we need to discover the ones that are nearby enough that we can study them in detail. It's interesting to watch a bird's nest from the ground and see the little birds high up there where you can sort of see them getting bigger over time. You can see how birds grow up. but to understand in detail how their colors change, how their feathers change, how their ability to move, to walk, to wobble, to eventually fly, to understand how all of that happens, you want to stick a camera right next to the nest. Well, for us to understand how stars die, we want to stick a camera right next to the supernova, but not too close. And so what we want is to understand how stars in the nearest galaxies explode. And those are getting discovered by amateur astronomers who are going out and who are looking up. This is the Reverend Bob Evans down in the bottom corner. I love his name. He's an Australian. He's in his lifetime discovered by eye. I think this number has actually gone up to over 40 supernovae since I made this slide. He's memorized the sky. He scans every night from galaxy to galaxy to galaxy to galaxy, looking to see if any of these galaxies changed, to see if a new star blew up that he was able to discover and call in and report so that people could study it in detail with bigger, better telescopes. There are CCD hunters as well, people who are using digital cameras. Mark Adams in the UK, Tim Puckett in Georgia, Michael Schwartz in Arizona, who are finding dozens of supernovae using cameras every single year as they image the sky and compare one night's images to the next. This is how we understand where elements come from. All of these people, again, working with the American Association of Variable Star Observers. But we're not the only game in town. We just have some of the coolest toys. We also partner with other people. In this case, we partner for the Center for Backyard Astrophysics. Many different types of stars explode. One other type that explodes are white dwarf stars. These are stars a lot like our sun that have lived their lives, stopped burning nuclear fuel in their center, and compressed down to about the size of the Earth's moon. But they happen to do this near another star. And they get a little close to that other star and gravitationally start sucking matter off of it. And due to this troubling thing called conservation of angular momentum, which makes all the math way harder than you ever want to solve without a computer, this matter coming in, spirals around the white dwarf, forming a disk. And occasionally, the amount of matter in this disk builds up to the point that the conditions in this disk are identical to the conditions in the center of a star. And the disk ignites like a million nuclear weapons going off at once. And we can see this as a new star in the sky, as a dwarf nova, as a cataclysmic variable. We have way too many names for this process that is really the same physics occurring in different ways all across the sky. Lots of people are trying to understand what is it that makes one of these go off every 60 days and another one of these go off every 60 years. And to try and understand the mechanisms of the exploding disk, to try and understand the mechanisms of the material getting ripped off of the companion star. People study these in radiolight. People study these with the Hubble Space Telescope. Now, the thing is, you don't want to point the Hubble Space Telescope at one of these things while it's in the process of exploding, because you will destroy the Hubble Space Telescope. Not something any professional astronomer wants to be responsible for doing. I think we'd be killed. So what you do when you get your time granted on the Hubble Space Telescope and you want to observe something that has the potential to explode and destroy the Hubble, if you look at it like looking at the sun with a digital camera you buy at Best Buy, what you do is you call up all your friendly neighborhood amateur astronomers and you say, could you keep an eye on this object? And if it starts to behave weirdly, call me right away. And so you have to have continuous observation for 1 full week prior to Hubble Space Telescope observations to confirm the star is not in the process of exploding. Now, at the same time, if you're observing this in radiolight with the Very Large Array out in New Mexico, you probably want to be seeing, well, what's happening while it is exploding? So there, at the same time, are other astronomers that say, hey, could you look at this object once a night, and if it's exploding, let me know so I can get my radio telescope pointed. Again, I as an individual can never get enough telescope time to monitor night after night all these different objects from the ground. But I can go to the backyard astronomers and say, hey, can you help? And they do. This is an odd object. We don't know what it is. It's called Epsilon Aurigae. And you can sort of make out bad data points here. The data is perfectly good. The color of the points is the bad part. This is a chart that I stole from a paper that was written back in the 80s. This is an object that very rarely goes into this weird eclipse, where the star for 20 some odd years will be nice and bright and pretty, and then will suddenly get faint and then get bright again. And that's the curious part, because normally you have an object passing in front of it. It does not pass in front, evaporate, come back, and go across the rest of the way. But that seems to be what's happening here. And the best way we know to explain this is you have a nice, friendly, bright star. You then have a disk, and I can't make a disk so well with my hand. You have a disk passing in front of it. And as the donut-y part of the disk passes in front, you get eclipse. But then when the hole starts to go in front, you get brightening again. And then when the other part of the donut passes in front, it gets faint again. We think that's what's happening. We think you have bright star, disk with small star inside of it, maybe a disk that's forming planets. And what we're seeing is that disk passing in front. Now, the last time this happened, back between 1982 and 84, we didn't have that many digital cameras. It was brand new technology. Even most professional observatories weren't using it. We didn't have the Hubble Space Telescope. We didn't have any space telescopes. Well, next year, in 2009, this object goes back into eclipse. And I invite all of you to help us, in celebration of the International Year of Astronomy, go out, look up, and figure out what is going on with this crazy object. Now, this is one object, but it's not the only one. You can also go out, and as I said before, you can go out and look up and see planets crossing in front of other stars. There's an organization called transitsearch.org. On its website, it publishes the times at which planets should be crossing in front of the nearest, brightest stars that happen to have known planets. We can tell if a solar system has more than one planet by looking for variations in when the planet we know about passes in front of that star. So over time, as we measure, okay, it goes across, it comes back, it goes across, but it's 3 minutes late. It goes across, but it's 2 minutes early. By looking for these slight changes, by looking for the amount of time it takes for the planet to pass in front of the star, we can measure all sorts of really neat characteristics of other solar systems. Again, this is completely new. We know of over 200 stars, or over 200 planets orbiting other stars now. And you can go out and look up and help us understand these alien solar systems. And then there's just cool stuff. Who doesn't want to see Mars passing behind the moon? But you can also go out and, cursor? There we go. You can watch asteroids passing in front of other stars. Now, it doesn't look this good. You cannot, in fact, see asteroids that clearly unless you are taking a space probe and putting the space probe near the asteroid. From the planet Earth, what you actually see is just the star disappearing. But what's kind of cool about it is you have small rock passing in front of really distant star. Small rock that always looks like a potato. And if you have someone on the south of the planet, they're going to look up across one part of the rock and see the star eclipse as it passes behind this part of the rock. Someone on the north might look and see this part of the rock. And we've all played with potatoes and probably peeled potatoes before, and you know they're not the same thickness at all parts. So you might have a crazy shaped one like that, where the people that see this part go across see a brief eclipse. People down here see a longer eclipse. So even though we can't see the asteroid, by getting people all across the planet Earth out looking up and basically doing all sorts of different surveying of this object that's millions of miles away, we can measure the shapes of asteroids from the planet Earth. And people do it in groups using ham radios. It's a community event where everyone's calling out, hey, I see it, now I see it. So you hand off the asteroid across the planet. Now, not everyone likes to go outside. It's kind of cold, especially here in Nebraska. I went to Michigan State. The weather was kind of similarly miserable come February, where really you just want tunnels everywhere. So if you want to get involved in science and you don't want to go outside, I understand. Here's a project you can do. This one's kind of boring, that's why I'm starting with it. It's called Stardust at Home. It's basically a mission to find dust. It's interstellar dust, which makes it cool. there was a space mission that went out, and it had this stuff called aerogel. It's the lowest density solid that we know how to make. And they exposed the aerogel to space, and based on calculations, they presumed that they captured order of 40 or 50 dust particles within this aerogel. They then brought it back down to the planet Earth, landed safely, and used a camera to scan across the aerogel, looking for the tracks of dust particles passing inside of the gel. And by focusing microscopes in different ways, you can actually focus at different levels within the gel and see the track moving through the gel. The only way to find these things, because there's also imperfections in the gel, is to use human eyes. Human eyes can see things that you can't program a computer to discern. And so they asked the people of the planet Earth, can you please help us find dust? And people sat at their computers and scanned through these pictures, which are boring and gray. I admit I'm not a fan of dust. But they did real science. And once those people found those grains of dust, they went in and removed the dust from the aerogel. And now there are scientists in labs studying pieces of dust that came from outer space, that have never been weathered, have never been rained on, that have never been processed by the planet Earth's chemistry. This is unpolluted dust created in the moments that our solar system formed. And that's what makes this dust cool. Now we're also inviting people to help us classify the surfaces of other planets. This is Clickworkers, a project to look at images of the surface of Mars and help identify. Some of you might be able to make out there's a very sad squiggly, whoa, cursor madness. There we go. There's the word dunes here, kind of sad. If you click on any of these different pictures stand for different types of terrain. And you can help scientists who don't have the time to look through all the millions of images classify the surface. You can go through and you can mark where craters are located. And this is actually kind of cool, because a section of Mars that's coated in bazillions of craters, that's an old part of the surface where nothing has come along and weathered away, eroded away the craters. The parts of Mars where there aren't craters, that's something new. That's someplace where wind, where water has changed the surface, and it allows us to date the surface and understand the geology of the surface of Mars. Now here's my favorite project. It's called Galaxy Zoo. Some of you might have heard about it. It actually hit the front page of MSNBC, CNN, and a bunch of other news sites a few months ago. This is a site, and this is the actual website here, and I lost my cursor, there it is, that asks you to look at galaxies. There's over 1 million of them in the system. To look at galaxies and click on them, or click on the type of symbol over here that looks the same, and to help scientists classify the galaxies. Most of them are orange blobs. Sometimes they're orange blobs shown in black and white pictures. But occasionally, if you click long enough, you'll get to see a family of galaxies. And in this case, you can make out this one has faint spiral structure. So I look at that and I go, it's anti-clockwise. And it says anti because this is a British project, and they don't say counterclockwise, they say anti-clockwise. And as you click through, what you're doing is helping astronomers understand the distribution of different shapes, different orientations of galaxies on the sky. And while most of what you click are orange blobs, there are occasional, and they give you a random assortment of almost 1 million galaxies. So sometimes you have to click a while. You'll occasionally find truly spectacularly beautiful objects, but apparently not right now because I have a live audience. So while I'm clicking on this, I'm going to tell you where this originated. There's a British grad student who was given an assignment to, by eye, look at 50,000 galaxies in 1 month and classify whether they were boring ellipticals, whether they were spirals that were edge-on, whether they were spiral galaxies that were rotating clockwise or they were rotating counterclockwise. Because if we live in a truly random universe, you should find that of the clockwise, counterclockwise, it's 50-50. You should be able to figure out, well, how many galaxies are elliptical to how many are spiral. He went through, he did the results. It came back not quite 50-50. His advisor was concerned. he was sent off and told, hey, could you look at another 50,000 more? This is also what happens when you let computers tell you what is a galaxy and what isn't. This is actually a satellite passing through the image. This is where you click star, don't know. The images in this were selected by a computer. Computers can say star, not star. That is all they can do with very good accuracy. In terms of going galaxy that's spiral, galaxy that's not spiral, galaxy that's blue, computers aren't so good at that. And so this is why we tortured poor innocent Kevin. Here you can see arms. And after he was told to go look at another 50,000, being British, he went to the pub. While at the pub, I learned a wonderful British word. He whinged. This is I don't know. Whinged is cringing and whining all at the same time. It's a wonderful word. And he complained in the company of other graduate students and postdocs. And one of them, a good friend of mine, Chris Lintott, said, well, why don't we just get the public? You are now the public. I, unfortunately, am also apparently, as I classify galaxies in front of you, trying to find something pretty. Why don't we get the public to look at these galaxies? And it's strangely addictive, because you know there's pretty ones here somewhere. So you just sit here and you keep, it's almost pretty, it's so close. You just keep classifying something in hopes that maybe you'll get something pretty. We're getting prettier here. It gets better. Maybe not tonight. There, I found something pretty. I'm happy. So you keep classifying, and you can see how terribly, horribly, awfully addictive this is. You sit and you classify. And the guys who came up with this idea, they figured it would be a side project. They'd have the computer tell them what the galaxies were, and once that cut was made by the software, they'd put it out on the internet 3 years later. Maybe they would have gotten 10 different people to look at each of the roughly 1 million galaxies. Within the first 24 hours that this website was online, they actually melted a server. I didn't know you could do that. Neither did they. One of the servers at Johns Hopkins University was getting hit by so many people trying to get in and classify galaxies that parts of it melted. They were able to get it back on within 7 hours. Within 24 hours, the public had done more classifications than Kevin in 1 month. Within 6 months, they had over 30 observations by 30 different people on each of the roughly 1 million galaxies. There are 30 different research projects, roughly, around the world following up on the results of this project. And for the first time ever, I got to use the word unique and actually mean it in a grant proposal. Because there is a Dutch school teacher, Hanny van Arken, who one day, while compulsively clicking in hopes of finding something pretty, while producing science, while exploring the universe, while perhaps seeing something that no one else ever bothered to look at with their eyes, she came across a curious little blob of glowing gas and asked, what is it? And she referred to it with the Dutch word voorwerp, which we thought was really cool. I wasn't there at the time. I still think it's a cool word, though. And the people who were working on the project, they said, we don't know. And so they've been following up on it. And they think they found a blob of gas that was illuminated by a giant angry black hole. It wasn't actually angry, but it was feeding. It was eating stars, gas, planets, whatever happened to fall into it. And while it was consuming matter, it emitted high energy jets. And one of these jets hit that blob of gas that's about 10,000 light years away. Now the crazy thing is, if you look at that galaxy today, you don't see that black hole giving off jets. Those jets turned off. But it's taken time for that jet to keep going through space. And the space where this blob of gas is located, the jet is still located, even though the black hole already stopped eating. This is a unique situation where for the first time, we have found a galaxy where we know the black hole just stopped eating stuff. And we have found a blob of gas where we know there was a jet of high energy particles. This project is out there for you to participate in. And in the next few weeks, we hope to be launching a Galaxy Zoo 2 website that will ask you to go out and make even more detailed classifications of stuff that is generally not always small, red, elliptical galaxies. We've increased the probability, and now I am part of the project, so when I say we, it's much more honest. We ask you to go out and look and help us understand all the crazy shapes that galaxies come out in. Now, galaxies aren't the only thing that you can look at and understand better than just random person using a computer where the computer is doing all of the classifications. A 5-year-old can be trained to visually say clockwise versus anti-clockwise for a galaxy better than you can program a computer to do it. We're going to take this technology, take this idea, and build new citizen science gateways. We're still coming up with a name. We've tried on Universe Zoo, Cosmic Zoo, Zoo of Discovery. We don't know what we're going to name the thing. But it is going to be a gateway of discovery for people to go out and learn more about the universe. We have built ties with the Lunar Reconnaissance Orbiter to allow people to classify the surface of the moon and look for craters that have formed since the Apollo era when it was last mapped in detail. The data from that series of observations is going to be used to figure out where NASA next lands men on the moon, and you can be part of exploring the surface and looking for that site. We have deals with the Messenger mission, which is just doing its latest flyby. The high-res images are just hitting the internet near you. In a few more months, that mission is going to go into orbit around Mercury, and we're going to invite you to go out and look at the surface of Mercury and look for the cracks that formed as the planet contracted as it cooled, to help us look for cratering, to help us understand the surface of this planet so close to the sun. We're working with other missions as well. Over the next 3 years, NASA funding willing, we're going to be introducing at least 4 new citizen science projects to help understand this universe using citizen astronomers, like anyone in this room, like 5-year-olds even, can do citizen science. And so I invite you to join us. And next year in particular, I invite you to join us. Next year's the International Year of Astronomy. It's a UN-endorsed event where we invite everyone in the world to go out, look up, and celebrate the universe, because it's yours to discover. Here in the United States, we have a variety of different programs where I'm lucky enough to be part of the United States staff that is making this possible. Our projects are highly varied, everything from a 365 Days of Astronomy podcast that does everything from culture to history to the latest discoveries to the Epsilon Aurigae, the donut passing in front of a star that I told you about a few minutes ago. That's another International Year of Astronomy sponsored event, to work trying to protect dark skies, to we're even getting planetarium shows created, and we're building telescopes that we hope to sell that will be higher in quality than the one Galileo used and will sell for under $10 a piece. Instead of having the one child per computer, we're going to have one telescope per computer. It's our dream. We're still raising money. If there are any rich people in the audience, please contact the American Astronomical Society to make your donation. I'm sorry, I'm a member of staff. I'm required to say that. But next year, we will force you to learn astronomy. You have no choice. This is sponsored by the UN. You will learn. You will look up. So please join us. The universe is yours to discover and yours to do real science as you explore it. If you'd like to learn more about any of these things, I live on the internet. I'm really a virtual person. I'm just a figment standing up here in front of you. I do the Astronomy Cast podcast, and I also blog at starstrider.com. Check out either of these sites. Astronomy Cast puts out a weekly 30-minute audio podcast. It's available in iTunes. Starstrider, it's just a blog. It's all about my life as an academic exploring astronomy. Check it out and learn more, and have a great night. So I think this is the point where some of you escape and others of you ask questions. Yes?
How often is a gamma ray burst detected?
Okay, the question is, how often is a gamma ray burst detected? It depends. In theory, we should be getting at least one a week, sometimes once a day, but sometimes random doesn't work so well. Let me go to a website where we can actually see the most recent bursts. There is a gamma ray burst real-time sky map at Sonoma State University that you can go out and you can see here that there were bursts on the 11th, the 8th, the 7th, the 3rd, the 28th, the 23rd, the 22nd. These are just ones that were detected. There we go. So you can see here that anything that's less than 7 days is blinking at you. Greater than 7 days and less than 60 is in dark blue, greater than 60, but still worth not falling off of this sky map is in light blue. So they're going off and being detected all the time, and that's kind of cool. Yes? The question is, what telescope are they currently using for this? The dedicated systems are the US SWIFT satellite and the European HETI mission. Other questions? Yes?
As a teacher interested in getting my students involved in citizen science, when they generate data, do they then have access and a record of the data they generate?
Yes.
So that we can also look at it?
Yes, so he said, as an educator, do they have a record of what they've looked at, and as an educator, can you get at it? You are the reason I wrote grants. So currently, anyone who goes in and uses the Galaxy Zoo website can get a record of what they've looked at. They can see what are the things they've classified. They can go back and visit their favorite objects. But as a teacher, you can actually start to use this to teach statistics. If you have 30 kids in your class and you say each of you click through 30 galaxies, 30 times 30, well, you're building a large sample quickly. You start to be able to do statistically significant data analysis within your classroom. NASA grant willing. We are going to be building an educator's interface to the Galaxy Zoo portal such that an educator like yourself can go in and say, hi, I'm a teacher, please give me 30 interrelated logins, where the student logins will act just like a normal person login in the first version. But you as an educator will have access to everything they've done so that you can pull that in and show the statistical significance and also make sure that like little Johnny isn't purposely clicking the wrong thing every single time. Now the next step of this is we're also going to work, this was done by a couple of grad students and postdocs looking to do strictly science, and that's the power, this is science. This is people discovering things through real original research. They're learning things the same way we originally learned them. Within the first day that Galaxy Zoo was up, people realized elliptical galaxies are typically red, and you get blue arms on spiral galaxies. That's something we make students memorize when they take Astronomy 101. People doing Galaxy Zoo figured it out on their own to the point that they started, anything that was red, they didn't even bother to look at it closely. It was elliptical. And so that's why there's now black and white images. It's to try and get a catch on are people judging based on color or based on actual shape. So we're also going to be adding educational materials which aren't there currently, NASA funding willing, that will allow you as an educator to mandate that little Sally must read the following activity and do the interactives before she's allowed to go on and classify more galaxies. That's where we're headed, is we want to add the educational framework to support teachers who are trying to bring this into their classroom. For now, we have forums, and there are lots of teachers out there on the forums. And they, in many cases, have created educational materials, and they're willing to share. Other questions? People in the back. Oh, come on, it's astronomy. You have some, how often do you get, well, here you have PhD astronomers, but.
What about that telescope in Boston? How did they do that? The high school telescope?
The high school telescope, let me flip back to that image. They are using a process called drizzle. It's actually the same technique that was first used to image the center of our galaxy. What you do is extremely high-speed imaging. Our atmosphere, the reason we see stars as twinkling is because our atmosphere is constantly changing, constantly moving. There are pockets of hot and cold air moving past one another. And as the light passes through packets of air that are different temperatures, it's just like passing through a series of little lenses, and it causes the light to constantly bend. And if you're taking images over time, as the atmosphere moves, the light first might get bent over here, then it gets bent over here, and it creates a smear on your detector. Well, you can get around this by using high-speed imaging and only looking at a small area of your detector and assuming that everything within that small area of your detector has been moved in the same way. So you take high-speed images, and then you align the brightest point to align these high-speed images of things that are moving. And then when you stack all of these short exposures together, it's the same thing as taking one really long exposure. And so you're able to synthetically take a couple-minute exposure of the International Space Station as it moves rapidly across the sky. And that's just cool. Other questions? I see lots of students, and none of you are asking anything, but you stayed.
Let's thank our speaker again.
Thank you very much.